right. So let's go down here to the next section, right? And it talks about some different reactions of benzene. Can somebody, if you watch the video, can somebody tell me what's necessary in order for benzene to react?
It needs a catalyst.
Got to have a catalyst. Benzene is so unreactive that the only way you can get it to react is by using a catalyst to make it react. Is everybody familiar with what a catalyst is? Did y'all learn that in GChem Part 2 about catalysis?
Up the reaction.
Yeah, what does it do?
It speeds up the reaction.
Increases the rate by doing what?
Increasing the activation energy.
Increasing it or decreasing?
Decreasing.
Yeah. So a catalyst decreases or lowers activation energy. That's the purpose of it, right? And so when you look at benzene by itself, you might initially think, well, it's got pi bonds, so it'll react just like any pi bond containing molecule, but it doesn't, right? This is a very inert molecule. You can beat on it forever and it won't react, right? But one of the things that it does do is what we call electrophilic aromatic substitution, which is right here, right? There are two types of substitution you can do on a benzene ring. You can do nucleophilic. I'm just going to abbreviate it. You can do nucleophilic aromatic substitution, or you can do electrophilic aromatic substitution, which is what we're going to focus on. With nucleophilic aromatic substitution, the ring acts as an electrophile. Right? In electrophilic aromatic substitution, the ring is a nucleophile. Right? So you're going to use one of those pi bonds from the ring to attack some nucleophile or some electrophile, I'm sorry. All right. Any questions about that? So you have two types of substitution that you can do on a ring. Both of them involve removing or substituting, one of the hydrogens on the ring, right? If you notice right here, see this, there's a hydrogen at every carbon on every vertex on this ring. Right, so what I did in effect was substitute this hydrogen with bromine. Is that right? So I swapped it out. Anybody not see that or have a question?
No.
Okay. So we're going to talk about this one mechanism, and then from that mechanism, we're going to be able to determine the mechanism for any electrophilic aromatic substitution because they all follow the same pattern. All right, so let's take my benzene ring. Come on, man.
Dr. Russell, is that printout on your on the website?
It's on Blackboard. Yes, it's right underneath the the conjugated dienes handout.
Okay.
Yeah. So I'll take this plus BR2, and that's going to give me this. I better I'm gonna move my pi bonds around to make it coherent.
Can you zoom out a little bit? I can't. Your ring is cut off. Okay, that's better.
All right. So there's 3 steps to this mechanism, and there's 3 steps to all of these mechanisms. The first is to prep your electrophile. That's the purpose of the catalyst. Right? It makes the electrophile more reactive. So in this case, what happens is, and you always do these type of halogenation reactions, normally you do it with an iron catalyst. So in this case, we're going to use iron 3 bromide. right? So what happens, you have your bromine is going to coordinate to iron. Do y'all remember that from part 2 of CHEM about metals coordinating to non-metals? Basically, bromine has a bunch of electrons around it, right? It's got 3 lone pairs. So it can actually take one of those lone pairs and donate it into an empty orbital on iron. Right? So once this coordination or this complexation happens, I'm actually going to, I don't need the battery to die now. This is actually what's going to be my electrophile. All right. So then in the next step, once I prepare the electrophile, the second step is for the ring to attack it. All right. So here's my ring. Here's my electrophile. So the ring is now going to attack here and break not do that. Break the bromine bond, and those electrons are coming here. Right, so I end up with a cation and a negatively charged iron complex. All right, so there's a plus charge on this carbon right here. All right, any questions? Go ahead.
The other double bond is still there, right?
Which one?
It was one by the BR. It was 3 in the ring.
Yeah, I just used one of them to attack the bromine, though. You see right here?
Oh, okay.
Right, this one right here, I used to attack the bromine.
Okay.
It don't help that my ring looks like a Pac-Man monster. Right, so now that one is that broke, and then this is a common intermediate to all of these reactions. You get this what's called an uranium ion. So this is this is where I have to do my final step on, right? So the final step is to what? Anybody who watched the video, if you want to sleep already. That means everybody was asleep.
Oh, what did you ask, Dr. Russell?
I asked what the final step was.
You're gonna take the negative charge and attack the positive.
Are you gonna attack the positive, or are you sure about that? What I want to do is get my ring back to being aromatic, right? And so what I'm going to do to reestablish aromaticity, I'm just going to redraw this, is I'm going to do an elimination. There's a hydrogen here on this carbon with bromine.
Does it deprotonate the ring?
Yes. Yeah. So you end up here. And then these electrons come here. So it's like an elimination. It's like an E1 type elimination almost. So you end up with this as your product, right? The reestablishing aromaticity is a big step because you lose a lot of energy when you break up that aromaticity. So it's not plus HBr plus FeBr3. Oh, that's sloppy. Yeah, you lose a lot of energy when you break the aromaticity of an aromatic ring up. All right.
Can you zoom out, Dr. Russell?
Is that better?
Yeah, I'm talking about. Can you just, like show the parts 1 and 2 of the halogenation? Yeah, that's good.
Yeah, so the first step is to prepare your electrophile. And depending on the electrophile, that step is going to be different, like in every case. The second step is for the ring to attack the electrophile, or at least either the electrophile or the complex, right? In this case, it's still complex to iron. So once the ring attacks, you make an intermediate iridium ion, and then after that, you deprotonate the ring with using the iron bromide, iron tetrabromide. And I don't know if you can see that arrow, so I'm gonna draw it in a different color. All right, any questions about that, the mechanism there?
Okay, could all the pi bonds attack equally?
Yes, any one of them can attack. Yeah, they're all susceptible to attacking the electrophile, but I just did that one for clarity.
Okay.
Yeah.
We would get like 2 different products, though, right?
Well, no, because if you look at the ring, the aromatic ring, it doesn't matter where you put bromine on it. All you would have to do is rotate it. Let's put bromine up here. Right, I can just rotate this thing around in space to make it look just like that.
Okay.
Yeah, it does. It'll be now. The only time you'll get different products is if the ring is substituted, and we're going to talk about that too. But if it's an unsubstituted ring, it doesn't matter where your electrophile ends up. It's always going to be the same thing. All right. Any other questions? So let's go back up to here. All right. So the main reactions we're going to talk about are here. Right. Halogenation is one of them that we just showed. And then alkylation, Friedel-Crafts alkylation, and then Friedel-Crafts acylation. Right. Those are those other two reactions we're going to talk about and talk about the mechanism. And then we're going to talk about nomenclature, and then we'll probably stop before we get to ortho and para effects. Was that in that video? Ortho and meta and para?
No.
Really? Okay. I have to make sure I let me check right quick. Hold up. Because I know I have a video discussing that. I just need to make sure I sent the right. Well, the one I sent last night was the right video, but there's another video discussing directing effects. I want to find that first. And I'll chop this out of our recording. So come on. I don't know why my computer's been so slow lately, man. Good night. All right, while I'm doing this, are there any questions about the mechanism that we just did?
No.
All right.